Hello everyone, welcome back. So in today's video, we'll take three problems from mechanics. So the first question is based on the topic of motion of center of mass. So let's first read the problem statement. So in the first paragraph, they're saying, according to the principle of conservation of momentum, if the external force acting on the system is zero, the linear momentum of the system will remain conserved. It means if the center of mass of a system is initially at rest, it will remain at rest in the absence of external force. That is, the displacement of the center of mass will be zero. So what they're saying is if I take any system of particles, and if it is given that the net external force acting on the system is zero, then that is essentially just saying the total mass, the mass times the acceleration of the center of mass is zero. And if it is given that VCM is also zero, so and then what we can say is if VCM and ACM are both zero, then the displacement of the center of mass is also zero. So this is pretty obvious. If the particle doesn't have any, if the center of mass doesn't have any velocity or acceleration, it just can't move, right? So that's what the first paragraph is talking about. So the second paragraph tells us about the question. So we have a plank of mass capital M. Okay, so this is the plank and it is placed on a smooth horizontal floor. Two light identical springs, each of stiffness K, are rigidly connected to the struts at the end of the plank as shown in the figure. Okay, so these are the struts and they are rigidly attached to the plank, which means they can't move relative to the plank. Now, when the springs are in their unextended position, the distance between their free ends is 3L. A block of mass capital M is placed on the plank and pressed against one of the springs so that it is compressed to a length L. So initially, there was no mass here. So this spring over here was uncompressed. And while it is in its natural length, the spring was something like this, such that the distance between the two springs was equal to 3L. Okay. Now what we did is we brought a mass and compressed the spring by a distance of L. And then to keep the block at rest, it is connected to the strut by a means of a light string. Okay, so then we connected a string between the mass to hold the mass M in place. Okay, initially the entire system is at rest. Okay, and now it's given that the string is burnt. And we have to talk about the maximum displacement of the plank, maximum velocity of the plank, and maximum kinetic energy of the block. Okay. So give this problem a try, guys, then check out the solution. Okay, so first let's start by drawing a diagram. Okay, so this is the diagram of the situation after the string is burnt. Now as the spring is compressed, it's going to push on this block of mass M, and it will also push on this strut over here. So a few pointers before we begin, we can see that initially the velocity of the center of mass is zero. Okay, and the second thing is that the net external forces taking the entire system together, which means all the springs and both the masses. So if we take all of them together, the net external force on the system is zero. From these two, we can conclude that the position of the center of mass is fixed. Okay, which means the center of mass won't move. So for example, let's say I say that the center of mass is somewhere over here, then throughout the motion, the center of mass will always be over here. Okay, so once that is clear, we only need to care about the x coordinate of the center of mass in this question because the y coordinate is not changing anyway, right? The definition of the x coordinate of the center of mass is m1x1 plus m2x2 divided by m1 plus m2. Okay, where x1 and x2 are the position of mass small m and capital M with respect to some fixed origin. Okay, so we can choose the origin as we wish. So let's just say the origin we want it to be somewhere over here on the ground. Okay, now it doesn't really matter where the origin is, because if I take the change on both sides, which means if I want delta x COM, so it will be m delta x1 plus capital M delta x2 divided by small m plus capital M, right? But I know that the x coordinate of the center of mass does not change. So this thing would just be zero, which means m times delta x1 plus capital M times delta x2 equal to 0. Okay, so now this particular equation over here deals with delta x1 and delta x2. Now delta x1 and the delta x2 is just the displacement in the x direction, which is just the change in positions, right? So initially, let's say mass M is over here, and finally, let's say it's somewhere over here. So this is going to be delta x1. And let's say in the same time, if capital M moves towards the right by delta x2, then we can say delta x1 and delta x2 are related by this equation. Okay, so now in the first question, they're asking us about the maximum displacement of the plank. Okay, so basically they're asking us what is the maximum value of delta x2. So another fact that we need to talk about is that the velocity of the center of mass was equal to 0, right? So this would mean that small m times its velocity plus capital M times its velocity should be 0. Okay. So now we know that capital M will start moving towards the right. Okay. So its maximum displacement or delta x2 max will basically be when v2 equals 0, right? So it will start moving to the right and it will stop when its velocity is 0. So in short, delta x2 will first be maximum when the velocity of the plank becomes 0. Okay. But according to this particular equation, we can say that if v2 is 0, then v1 also should be 0. Okay. So the initial kinetic energy of the system is 0 and the final kinetic energy is also 0. But we know energy is conserved here, right? So what is the initial stored potential energy in the spring? It is half k L squared, right? Because the spring initially was compressed by a distance of L. So if the initial spring potential energy is half k L squared, then by energy conservation, the final spring potential energy should also be half k L squared, because we can say ki plus ui should be kf plus uf. From looking at these equations, what we can infer is that finally, when both of them come to rest again, this spring over here on the left will also be compressed by a distance of L. So let's try to draw the diagram of that situation. Okay, so let's say this black dotted line that I just drew is the initial position of capital M, and let's say it moved towards the right by an amount of delta x2. Now we know that final compression on the left spring will be L, right? So what will happen is this mass will move towards the left, hit the spring and compress it by a distance of L. So it compressed the spring by an additional distance of L. And obviously the right spring will now be in its natural length. So this spring over here will look something like this. Okay. Okay. So now this is the situation at the time when the displacement of capital M is maximum. So both the masses are now at rest again. And now once again, the mass M will move towards the right. Capital M will move towards the left, and exactly the same motion as before will continue. Okay. So if you observe, this red line that I'm drawing is the initial position of this mass M on this plank, right? Okay. So now we want to figure out what is delta x2. Okay. So we'll write down our first equation once again. So M delta x1 plus capital M delta x2 should be 0. If you observe, this line that I just drew was the initial position of small m, right? So the small m covered a distance of L plus 3L plus L relative to the plank. So delta x1 relative to the plank is equal to 5L towards the left, right? But the plank itself moved towards the right by an amount of delta x2. So as I assume delta x2 is towards the right, delta x1 must be towards the left. So this would be equal to 5L, which is the relative displacement, minus delta x2. Okay. So basically if I go back to my original diagram, relative to this plank, small m moved towards the left by an amount of 5L, but the plank itself moved towards the right by an amount of delta x2, right? So the final position is going to be 5L minus delta x2 towards the left. Okay, so that's what I did over here. So now once we're done with this, what we can do is, okay, so let's say every displacement towards the right is positive. So we can say m into delta x1 would be negative here. So minus 5L minus delta x2 plus capital M times delta x2 should be equal to 0. So from here, delta x2 turns out to be this particular value. So that corresponds to option B. Okay, so now the second question is asking the maximum velocity of the plank. Okay. Okay. So for this, what I'm going to do is I'm going to say the velocity of the capital M mass is V. Okay. So then we can find the velocity of small m in terms of V using the fact that VCOM was equal to 0, right? So we can say small m into, let's say its velocity is V dash plus capital M into V equal to 0. From here, V dash turns out to be minus capital M by small m. Okay, it's negative, meaning the negative sign just means that it's towards the left. Okay, so let's say if this is V dash, so V dash in terms of magnitude is equal to this particular value. So I'm just going to get rid of the minus sign. So now obviously here, if we want the maximum value of V, that will be achieved when v dash is also maximum, right? Okay, so now obviously guys, the entire motion is just an interplay between the spring potential energy and the kinetic energy, right? So okay, so let's take this particular instant when this spring on the right is back to its natural length, which means the block is somewhere over here. So this, in this situation guys, so what's so special about this situation? Here the spring potential energy is equal to 0, which means the entire half kl square spring potential energy is now converted into the kinetic energy of small m and capital M. So, so this particular situation where half small m v dash squared plus half capital M v squared equals half k l squared. This is the situation when the kinetic energy of the system is maximum, because after this what will happen is small m will go hit the spring and it will start decelerating, right? So this is the situation when the velocity of the plank is maximum. So here, so now as we want v, we'll substitute for v dash. So, and after doing a little bit of all algebra, we'll get this as the velocity. Okay. Okay, so now the third option is asking us what is the max kinetic energy of the block. So this is quite straightforward. So that will just be half m v dash squared, because we just figured out this is the instant when the velocity of both the block and the plank is maximum. So this is just going to be half small m v dash squared. Okay, so after substituting v dash in terms of v, you'll get the answer as this particular value. So the answer to this question will be just B, C, and C. Okay. So now let's move to the next question. So question number 2 is from Pathfinder, and this is from the chapter Work, Power, and Energy. Okay. So this question is very frequently asked in a lot of test series. So let's see the problem statement. So we have a disk whose mass is capital M, and it is connected with two disks whose mass is small m, and they're connected with the help of two light inextensible threads. Okay, and each of their lengths is L. Now, initially the system rests on a frictionless horizontal floor with centers of the discs in a straight line and the threads straight. Okay, so now the middle disc is projected along the floor with a velocity of u perpendicular to the threads. So we have to find the tensile forces in the thread when the end discs are about to collide. Okay, so basically as capital M starts moving vertically up, it'll pull the smaller masses together, and the smaller masses will start approaching each other. And after a while, what will happen is that the capital M mass, the smaller masses will be just about to collide. So we have to find the tension forces at this particular instant. Okay. So first, let's start by drawing a diagram. Okay, guys. So let's say this is the initial diagram, and it's projected upwards with a velocity of u. So again, we are going to work with the center of mass frame here, just because of the same fact we used in the previous question. And that is the net external force is 0 if we take all the three balls together as a system. But in this question, different from the previous question, we have an initial velocity, which means the initial velocity of the center of mass is capital M. So this is capital M mass, and these are smaller masses. So the initial velocity of center of mass will be capital Mu divided by capital M plus 2m in the vertically upward direction. So this, if you substitute it, comes out to be 1 meter per second upwards. Okay. So I'm just going to directly write everything over here. So so in the center of mass frame, what we have to do is subtract VCOM from each of these masses. So U was 2 meter per second upwards. So if you subtract 1, it will have 1 meter per second. Similarly, the smaller masses will have 1 meter per second downwards as the initial velocity. Okay. So this is observing with respect to the center of mass. Okay. So now as we moved on to the center of mass frame, now the center of mass will remain at its place. So initially the center of mass was over here. Finally, also it will be over there. So another fact here is that the velocity of the center of mass in the center of mass frame is obviously 0, right? So, and it will be 0 at all instants. Okay, which means in the final situation when the two smaller masses are about to collide, even in that situation, the velocity v final of the center of mass will also be 0. So now let's draw a diagram of the final situation. Okay, so this is the final situation. So this is the situation just before collision, right? So So we know the fact that the velocity of the center of mass is 0. So first let's talk about the y direction. If I say that capital M has some vertical velocity, then by string constraint, or that is basically the length of the strings must be constant, right? So the velocities of the small m mass must also be v upwards. But this is not possible, because if I assume that each of these masses is moving with v upwards, then the vy of the center of mass will be non-zero, which is not true, right? Because in the y direction, the velocity of the center of mass is 0. Finally, what will happen is all of their vy will become 0. That's the only possibility. But they will have some approach velocity, let's say v1 and v2. I mean, by symmetry, we can see v1 equals v2, but the true logic lies in the fact that Vx of the center of mass is 0. So let's say if these balls had a mass of m1 and m2, so then what you will do is m1 v1 equals m2 v2. But here, as the masses are equal, we can see their velocities will be equal and opposite. Okay, so this situation, so this diagram over here represents the final situation. Okay, and this was the initial situation. Again, the question originally wanted us to find out this tension. Okay, so now we can figure out v by just conserving energy between these two situations. Okay, so let's do that real quick. So from here we'll get v square equals to, or v equals √2 meters per second. Okay, so we figured out what is the final velocity v. Okay, so now coming to another very important point. So the string length was given to be equal to L. Here we cannot write T equals mv squared by L. Okay, and the only reason for that is that this point over here is actually accelerated. Okay, so let's just see over here in this diagram. So here, observe the capital M mass for a second. It is being pulled by a force of T plus T, which is 2T, right? So it has an acceleration of 2T by capital M in the downward direction. So which means this point over here has the same acceleration of A in the downward direction. So let's just call this particular point as point number 1, and the point where the smaller mass is, let's call that point as point number 2. So acceleration of point 2 relative to point 1, this is going to be, this we can write it as v square by L in the j cap direction. Okay, and I'm assuming j cap, positive j cap in the vertically upward direction. Okay, but acceleration of 1 is actually minus a in the j cap direction. Okay, which means acceleration of the mass small m in the ground frame is v square by L minus a in the j cap direction. So basically, if you want to do it quick, relative to a, we can see the particle is moving in a circular path of radius L. So we can write, so its acceleration is v square by the radius of curvature a, which is L, right? Okay, then we'll add the acceleration of point 1 vectorially, which is a downwards. So effectively, its acceleration is v square by L minus a in the upward direction. Okay, so let's draw the diagram once again. So the acceleration of capital M is equal to a, which is 2t by capital M, and the acceleration of both the small m masses is equal to v square by L minus a in the upward direction. Now you can either use the FBD of small m, or you can just use the fact that the acceleration of the center of mass in the y direction is 0. So this would mean that 2m into v square by L minus a. So this is, so how did I write this? So this is just sigma mi ai, right? So I did, so this is m times a plus m times a. So that is why I wrote 2m here multiplied with v square by L minus a and minus capital M times a. Capital M is accelerated in the downward direction. So this would be equal to 0. Okay, so now all we have to do is solve it a little bit. Okay, and after solving, the tension T comes out to be 2 newtons. Okay, so that was it for this question. Now let's move to the next one. Okay, so the next problem is CYU3 from work power energy. So here we have a dumbbell that is constructed by 2 small balls of mass M attached with the help of a light rod whose length is L. and it stands vertically on a frictionless floor, touching a frictionless wall as shown in the figure. So if the lower ball is gently pushed away from the wall, the dumbbell begins to slide. So denoting the acceleration due to gravity by G, we have to find the speed of the lower ball when the upper ball is leaving the ball. Okay, so let's draw a diagram and try to understand what they're asking. Okay, so let's say this is the situation and the x coordinate of this mass, and let's say the mass on the ground is at a distance of x, and this particular mass is at a distance of y. And obviously this is not the initial situation, so both the balls will have some velocity, but the question is talking about the situation when the upper ball is leaving the wall. Okay, which basically means the interaction force between the wall and this upper ball, it becomes equal to 0. So this is the instant that they are talking about. So what is interesting about n equals 0 is that the acceleration of the center of mass in the x direction will also be 0, because there is no force in the horizontal direction, right? If you take if you take the entire thing as a system, the FBD consists of this normal and their gravity and their weights, right? So there is no force in the horizontal direction, which means the center of mass will have a 0 acceleration in this particular situation. So the main idea is that the normal is 0. So now what we're going to do is we're going to use a property of right triangles. Okay, so and that is, so if I draw the median from the vertex containing the right angle onto the opposite side, then we know the median bisects the hypotenuse, which means both of them become L by 2. But the property is just that the length of the median will also be L by 2. And the proof for this is pretty simple. All you have to do is apply sine rule to both of these triangles and you can prove this. Okay. So I'm not going to get into the proof, but I'm just going to use this directly. Now by the equal side equal angle property, if this angle is also going to be theta. Okay. So now this property tells us something important. The distance, and that is the distance of the center of mass from the vertex O, is a constant. So which basically means while both these balls are sliding along the ground, the trajectory of the center of mass is a circle of radius L by 2, which is centered at this point O. So now at this particular instant, the rod will have some angular velocity omega. Now this particular omega, which is the angular velocity of this rod, is nothing but the rate of change of this angle theta. Okay, so we can say d theta by dt is our omega. Okay, so now observe this median, guys, which connects the vertex to the center of mass. Okay, so that it makes an angle of theta with the vertical. Now d theta by dt is what is omega, which means the angular velocity of this median is also equal to omega. It's just in the clockwise direction. So because here if you observe the theta is in the clockwise sense, counterclockwise sense, but here the theta is in the clockwise sense, right? So the omega will be in the opposite direction, but its magnitude is going to be the same. So the use of this is that this is my vertex O and this is my center of mass. As I know the center of mass is going to be performing a circular motion about our vertex, the radius of who is L by 2, I can say the velocity of the center of mass is nothing but L by 2 omega, where omega is the angular velocity of this line. Okay, so using this geometrical result, we can directly figure out the translational velocity of the center of mass. So what's the total? So now the total kinetic energy of the system, we can write it as the translational kinetic energy of the center of mass, which is going to be half total mass into velocity of center of mass squared, plus the rotational kinetic energy, which is half ICM omega squared. So the moment of inertia about the center of mass axis is ml by 2 squared plus ml by 2 squared. So this is just going to be ml square by 2. So this will be 1 by 4 plus 1 by 4. So this comes out to be ml square omega square by 2. Okay. Now the decrease in potential energy. So if you observe this mass, initially it was at a height of L and now it is at a height of L cos theta. So the drop in potential energy is going to be mgl times 1 minus cos theta. So here we can cancel out some stuff. And after cancelling out some stuff, we get the omega square as this particular value. So we figured out the angular velocity of the rod as a function of theta. So now why did we do this? The main purpose was ultimately we wanted to use this particular fact, and that is the acceleration of the center of mass in the x direction is 0. So this we can also say that the rate of change of the x component of the center of mass with respect to time is 0. So if we can find out the x component of velocity of center of mass, we can just differentiate it with respect to time and set it equal to 0. Okay, so that will give us the required condition. So as we discussed earlier, but we already know that the velocity of the center of mass is L omega by 2 perpendicular to our median. So, and the median itself made an angle theta with the vertical. So this particular angle is going to be theta as well. So from here, we can see that the x component of the center of mass is L omega by 2 cos theta. So now if we substitute the value of omega here, we'll get this particular value. Okay. So here, as you can see, it's a direct function of theta. So now we can just differentiate it with respect to time, or we can even differentiate it with respect to theta, because at the end we'll have to set it equal to 0, right? So we'll just do dvx by d theta and we'll set it equal to 0. Okay. So now instead of, maximizing Vx, we can just maximize Vx squared so that our differentiation would be simpler. So this would be 2gl times cos squared theta minus cos cube theta, right? Okay, so now we can just differentiate it with respect to theta and set it equal to 0. So this would be 2 cos theta times minus sine theta cos squared theta times sine theta. So I can cancel out a cos sine, and what I get is cos theta equals 2 by 3. So this is the value where Vx reaches its maxima, okay? Or basically where dvx by dt become equal to 0. Okay, so if I set cos theta equals 2 by 3 back, then I'll get the x component of center of mass as. So yeah, I made a slight calculation mistake, guys. So here there was L omega by 2. So I forgot to divide here by 2. Okay. So basically we'll just have to divide everything with 2. So basically Vxcom just becomes root of 2gl divided by 27. So, but what they wanted was the speed of the lower ball. Okay. Okay. So, but what we found out was the Vx of the center of mass. But that's fine, because at this instant we know the first ball has a vertical velocity, right? And let's say the velocity of the lower ball, which we want, is v. So now we can just use the formula for the x component of the velocity of center of mass just in the x direction. So we can say Vx com is m1 v1x plus m2 v2x upon m1 plus m2. So both of them have the same mass and one of the balls have no horizontal velocity. So this would just become v by 2, and the LHS is Vx. So v would just become twice Vx, which is just 8gl by 27 square root. Okay, so this would be our required answer in this case. Okay, so if so this particular geometrical property actually made the analysis very easy. So an alternate approach, which is going to be lengthier than this, would be to write the coordinates of the center of mass, right? So in terms of theta, and then you differentiate it twice and find ax. And once you find ax, you set it equal to 0. So that's like one way to do it. Okay. So yeah, that was it for this question. If you guys have any doubts, you can comment down below. If you enjoy the video, please do like, share, and subscribe. And yeah, that's it. Thanks for watching.